There's a bamboo tower that cools the air inside a building by 15 degrees without electricity, without refrigerant, and without any mechanism a modern HVAC engineer would recognize. The global air conditioning industry generates $270 billion per year, keeping you dependent on compressors and coolant to do what this structure does for free. The tower has been cooling buildings for 3,000 years. The industry writes the energy codes. Your electricity bill arrives every month. The structure is called a wind catcher. In Farsi, it is Bajir. Bad means wind. Gir means catcher. The name is precise and complete. It catches wind. It is a vertical tower, typically square or octagonal in cross-section, rising between 15 and 30 feet above the roof line of the building it serves. Its upper openings face the prevailing wind on all sides. Its interior is divided by partitions into channels that direct incoming air downward through the structure, across an underground water reservoir or moistened clay surface at the base, and upward again through the living space of the building below. The air cools as it descends. It cools further as it passes across the water surface. It enters the room at the floor level, already 15 degrees below the temperature outside, moving without any pump, any fan, any compressor, any refrigerant, or any source of energy beyond the pressure differential that wind creates naturally across a vertical column of air. The physics are not complicated, the results are not debatable, and the technology is not lost. It is standing in the desert cities of Iran right now, in buildings that have been continuously occupied and continuously cooled for over 3,000 years without a single electricity bill, in Yazd Plateau of central Iran, approximately 1,000 years before Christ. A builder is constructing a residential compound for a merchant family on the edge of the desert city that will one day be called Yazd. The summer temperature on the plateau reaches 113 degrees Fahrenheit. There is no river within 20 miles. There is no forest. There's no material for the kind of massive stone construction that holds cool temperatures through sheer thermal mass. There is wind. There's always wind on the plateau. The builder constructs a tower above the courtyard. He divides its interior into 4 channels using fired clay partitions. He aligns the openings with the prevailing northwest wind. He digs a shallow basin beneath the tower floor and lines it with clay. He fills it with water drawn from the Qanat, the ancient underground channel that carries snowmelt from the mountains to the city beneath the desert surface. The family moves in. The summer arrives. The tower begins to work. The room beneath it stays 20 degrees below the temperature outside. The merchant conducts business, sleeps, eats, and raises his children in a space that a modern real estate listing would describe as air-conditioned. No electricity existed. No bill arrived. No technician was called. The tower ran on wind and water and the understanding of how air moves through a vertical column. It ran for the lifetime of the building. It runs still. By 500 years before Christ, the windcatcher had spread across the Persian Empire from the Iranian plateau to the Nile Delta. Egyptian builders adopted the design and modified it for the northerly winds that blow consistently off the Mediterranean. They called it the Malkaf. Their version faced a single direction, scooping the prevailing wind into a narrow channel that accelerated its velocity before releasing it into the interior space below. Temples in Memphis and trading houses in Alexandria used them. The wealthier the household, the taller the tower. Height increased the pressure differential. Greater pressure differential meant faster airflow. Faster airflow meant greater evaporative cooling at the water surface below. The physics scaled perfectly with ambition. A merchant who could afford a 30-foot Malkaf lived in a building cooler than a merchant with a 15-foot one. The technology was the status symbol, not because it was rare, because it worked better the more seriously you built it. The Romans encountered windcatcher technology during their Egyptian campaigns and documented it with the careful attention they gave to any engineering solution worth stealing. Vitruvius, writing his 10 books on architecture in the 1st century before Christ, describes passive ventilation towers in his section on the orientation of buildings and the management of interior climate. He notes that structures in the eastern provinces of the empire employed vertical towers to direct wind through interior spaces, and that the inhabitants of those provinces reported interior temperatures significantly below those in comparable Roman structures that relied on wall thickness alone for cooling. Roman administrators in North Africa adopted the technology for their own residences. The knowledge crossed the Mediterranean and entered the engineering vocabulary of a civilization that built across 3 continents. By the medieval period, the windcatcher was the dominant cooling technology from Morocco to India. The city of Yazd in Iran, which sits in one of the hottest and driest desert basins on Earth, had developed the technology to a level of engineering sophistication that modern passive cooling researchers still study as a reference benchmark. Yazd today contains more than 200 functioning windcatchers. Some are estimated to be over 1,000 years old. They cool homes, mosques, water reservoirs called yakshols, and the covered bazaars where merchants traded across the Silk Road. The bazaars of Yazd are among the longest continuously occupied commercial spaces on Earth. They have been open for business, cooled by towers, for over 1,000 years without interruption. No compressor has ever been installed, no refrigerant ever charged, no electricity bill has ever once arrived. The towers work today exactly as they worked the day they were built. Here is the science that confirms what 3,000 years of human habitation already proved. The wind catcher operates on 3 simultaneous physical principles that compound each other's effects. The first is the stack effect. Hot air rises. A tall vertical column of air in a tower exposed to sunlight on its exterior walls creates a temperature and pressure gradient that pulls cooler air from below and pushes warmer air out through the upper openings. This effect operates even when wind is absent. It generates passive airflow through the building continuously as long as the exterior temperature exceeds the interior temperature. The second is the Venturi effect. Wind striking the upper openings of the tower is forced into a narrowing channel and accelerates. A wind speed of 10 miles per hour at the tower opening becomes 15 to 20 miles per hour by the time it reaches the lower channel. Faster airflow across the water surface below increases evaporation rate. Increased evaporation rate increases cooling. The third is direct evaporative cooling. Water evaporating from the clay basin or moistened surface at the tower base absorbs heat from the surrounding air at a rate of approximately 540 calories per gram of water evaporated. In desert climates with low humidity, this process alone reduces air temperature by 12 to 18 degrees Fahrenheit before the air enters the living space. A 2014 study published in the journal Energy and Buildings by researchers at the University of Sheffield measured the thermal performance of a reconstructed wind catcher system installed in a building in the United Kingdom. In conditions simulating a hot summer day, the system reduced interior temperature by 11 degrees Celsius, nearly 20 degrees Fahrenheit, without any mechanical assistance. Airflow rates through the tower matched those produced by mechanical ventilation systems, consuming significant electrical power. The researchers concluded that wind catcher systems could eliminate the need for mechanical cooling in buildings across a significant portion of the global climate range. The study was published. It was cited by passive building researchers in Europe. It was not cited by any American Building Code Revision Committee. It was not referenced in any International Energy Conservation Code update. The file was not opened. The codes were not changed. Here is what should make you furious. In 1952, the Air Conditioning and Refrigeration Institute was established in Washington, D.C. as the primary trade organization representing the mechanical cooling industry in the United States. Within 2 years of its founding, the Institute had established liaison relationships with every major American architecture school and was funding research grants through the American Institute of Architects. By 1958, ARI representatives sat on the technical committees of the American Society of Heating, Refrigerating, and Air Conditioning Engineers, ASHRAE, the body that writes the standards adopted into building codes across the United States and in over 100 countries. Of the 39 founding members of ASHRAE's Standing Committee on Ventilation Standards, 32 represented companies that manufactured or sold mechanical cooling equipment. Not one represented passive cooling research, not one had studied wind catcher technology, not one was asked to. The standards that committee wrote defined adequate ventilation as mechanical ventilation. Passive systems were classified as supplemental at best, unverifiable at worst. An architect who specified a wind catcher instead of mechanical cooling could not demonstrate code compliance without commissioning an independent engineering study costing more than the tower itself. The barrier was not technical, it was procedural, and it was designed that way. Carrier Corporation understood this better than anyone. In 1902, Willis Carrier invented the first modern electrical air conditioning system for a printing plant in Brooklyn, New York. By 1915, Carrier had founded the company that would dominate the industry for the next century. By 1950, Carrier was installed in department stores, movie theaters, office buildings, and hospitals across America. The marketing was precise. Air conditioning was not sold as a cooling device. It was sold as a health product, clean air, filtered air, scientific air. The word conditioning was chosen deliberately. It implied that unconditioned air was inadequate, that the air your ancestors breathed for 10,000 years in naturally ventilated buildings required correction by a machine that Carrier Corporation manufactured, and that your utility company powered. The framing worked. By 1960, air conditioning was not a luxury in American commercial construction. It was a building code requirement in most jurisdictions. A tower that moved air without electricity was not an alternative. It was a code violation. The bamboo wind catcher disappeared from Western architectural education, not because it was tested and found inadequate. It was never tested. It was never compared against mechanical cooling in a controlled study funded by a neutral party. It was declared irrelevant by the same process that declared creosote preservation primitive and cork insulation exotic. The people who profited from the replacement technology controlled the framework that defined what required replacement. Wind catchers did not fail a standard. They were never allowed to meet one. Then in 2015, something shifted. The Windcatcher Company, a British engineering firm, installed passive cooling towers in a primary school in Hammersmith, London. The towers were manufactured from glass-reinforced polymer rather than traditional clay and bamboo, but operated on identical physical principles. Interior temperature in the school's main hall remained 8 to 12 degrees Celsius below external temperature throughout the summer without mechanical cooling. Energy consumption in the building dropped by 63% compared to the mechanically cooled school building next door. The project won the Building Services Research and Information Association Award for Innovation in Sustainable Building Systems. It was covered by architectural press in the United Kingdom, Germany, and the Netherlands. The New York Times did not cover it. Architectural Record did not cover it. No American Building Code Committee reviewed it. The ASHRAE ventilation standard was not updated. The electricity bills in American schools did not change. In 2019, researchers at the University of New South Wales published a comprehensive review in Renewable and Sustainable Energy Reviews, documenting passive cooling tower performance across 43 documented installations in 12 countries. Average interior temperature reduction across all installations was 13.4 degrees Celsius below ambient external temperature. Average energy consumption was 0 kilowatt hours. Average maintenance cost over a 10-year monitoring period was $37 per installation. The review concluded that passive Windcatcher systems represented a technically validated, economically superior alternative to mechanical cooling across much of global climate range. The review was downloaded by researchers in Germany, Japan, Australia, and Iran. It was not discussed at any American Energy Code revision hearing. The $270 billion industry did not issue a response. It did not need to. The codes it had written in 1952 were still in force. Here is what you can do right now. Bamboo Windcatcher towers can be constructed for residential and small commercial buildings using materials available at any building supply store. Structural bamboo poles provide the vertical column. Interior channel partitions are built from lightweight clayboard or compressed earth block. The evaporative cooling surface at the base requires nothing more than a clay-lined basin and a slow water drip from a gravity-fed reservoir. The entire system for a single-room structure can be built in 2 days by 2 people, with no specialized skills for under $400 in materials. The University of New South Wales review includes dimensional specifications for towers scaled to different building sizes. The Energy in Buildings study from Sheffield includes performance data for temperate climates, where mechanical cooling is currently used for 4 to 6 months per year. Both studies are publicly available through Google Scholar. They have never been removed. They have never been contradicted by a peer-reviewed study showing Windcatchers to be ineffective. They simply sit in indexed databases, unread by the architects and engineers whose curriculum was written by the industry that cannot profit from a bamboo tower. If you own a home in a climate where summer cooling is a significant expense, the physics are on your side. The technology is documented. The materials are available. The barrier is not science. The barrier is not engineering. The barrier is the gap between what a code committee funded by Carrier Corporation decided to approve in 1952 and what 3,000 years of human habitation across the hottest cities on Earth already knew worked without asking anyone's permission. The towers are standing in Yazd right now. The same towers, the same wind, the same 15 degrees of cooling that required no electricity when the Persian Plateau baked at 113 degrees and no power line existed within 1,000 miles. They stood through the fall of Rome, through the medieval period, through the Industrial Revolution, through the invention of the compressor, through the establishment of ASHRAE, through every energy code revision that made their legal use in American construction more complicated than installing a system that consumes $600 of electricity every year and breaks down every decade and requires refrigerant that cannot be legally handled without a certified technician. Your cooling bill arrives every month. It has arrived every month since you moved in. It will arrive until the day you leave. And standing in the desert 8,000 miles away, built from clay and wind and the understanding of how air moves through a vertical column, is a tower that makes that bill unnecessary. It has been making it unnecessary for 3,000 years. It will still be making it unnecessary when the last compressor fails and the last refrigerant charge leaks into the atmosphere and the last ASHRAE committee member retires on a pension funded by the industry he protected. The wind still blows across the plateau. The tower still stands. It does not need a code committee. It does not need a utility company. It does not need a certified technician or a refrigerant license or a monthly payment to a corporation that decided in 1952 that you would never learn what the desert already knew. If this vault opens something for you, subscribe and hit the bell. Every like and every share preserves what they tried to erase. The next vault opens soon. The Badger does not advertise. It does not lobby. It does not fund curriculum committees or sit on code revision panels. It rises above the roofline in silence. It catches the wind. It does what it has always done. It waits for the builder who remembers that cooling a room was never supposed to require a bill.